Yeah.
Yes, sir, it's no. According to the start. Please go ahead.
Thank you. So very warm welcome to all the participants in the session 9. That is the third session. So we have today the third session, third day. That's session 9 is on the glacier monitoring using remote sensing data and techniques. So regarding of that talk, we have a very energetic and very dynamic speaker, Dr. Saurabh Vijay. So very warm welcome, Dr. Saurabh, here in this FDP. So before let's start to have a talk, I would like to introduce the Dr. Saurabh here. So Dr. Saurabh Vijay have a bachelor degree in the electronics engineering from University of Rajasthan, and after that he have an MTech degree in the remote sensing from the Department of Civil Engineering, IIT Roorkee. So regarding the MTech degree dissertation, he got the fellowship of that is called the Germany DET fellowship. Under that fellowship, he had done the master thesis on a remote sensing of the glacier at the TU Darmstadt University, Germany during the 2011 to 2012. And after that, he went to the go for the PhD, and he had done the PhD from the University of Erlangen, Germany in 2017. After the completion of the PhD, he moved to go for the some postdoctoral position and the research associate position. So in the postdoctoral position, first he had done the Technical University of Denmark as a postdoctoral, and the another position like as a research associate in the Center of Wide Polar Climate Research Center, Ohio State University, USA. So that two position after the research position had done the after the PhD, and after that he moved to the faculty position in the IIT Roorkee in the Department of Civil Engineering in the 2020, and that is his profile. And other than that, if we talk about his research interest, his research interest include the Earth observation using satellite remote sensing, particularly emphasis on the glacier monitoring in the high mountain region, including Himalayas and the Greenland. And he authored 12 publications in the world-leading journal in the area of the remote sensing, as well as he reviewed the number of the publications and reports also. And he also served as one of the project member in the NASA project in the panel member. And he has initiated several India abroad scientific partnership, also member of this partnership in the India abroad membership. And in the IIT Roorkee, he taught the remote sensing course, GIS, GNSS serving course for the UG and PG both, as well as currently he's supervising PhD thesis as well as the MTech thesis. So his talk is on glacier monitoring using remote sensing data and technique. So now I am handing over to this session to Dr. Saurabh Vijay. So Dr. Saurabh Vijay, please.
Thank you very much. I think you can stop sharing now.
Yeah, please. Thanks.
Okay. So I share my screen one more time.
Yeah.
I hope you can see my screen.
Yes.
I can make it. Okay. So a very good afternoon to all of you. My name is Saurabh Vijay, and before we start, I would like to extend my thanks to Gopal Das for such a nice introduction, and Hitesh, who was also associated with IIT Roorkee and the organizers of this faculty development program on use of GIS and remote sensing in agriculture and natural environment. So I am presently working as an assistant professor at IIT Roorkee. And in the last 7-8 years, I have been using remote sensing data mostly to study glaciers in Alaska, in high mountain Asia, including Himalayas. And in the recent time, the last 3.5 years, I started working in Greenland as well. So, these locations are, very hard to access, and remote sensing plays a major role here so that we can monitor, because glaciers, as you would understand during my presentation, actually hamper our lives and also influence as well in a good way too. So we need to monitor these dynamic body of ice mass And in this talk, I'm going to discuss about what are the data and techniques that we use to monitor these glaciers across the world. So let's have a look. So I mean, this is my academic background, which actually already Gopal Das has mentioned. In the last 9 years, I have been traveling across the world and meeting people, gaining my knowledge in this direction. And I think it has been a very useful and important experience that I got, so that I can monitor glaciers, not in high mountain regions, but also in the polar regions as well. So let's have a look. So that is the outline of my presentation. First of all, I would like to introduce you to the Indian Karakoram and Himalayan region. I suppose that all the faculty members who are interested to study glaciers, they would actually start observing glaciers in the Indian Himalayas, right? And of course, then you can extend your work to the polar regions as well. So we start from the Indian Karakoram Himalayan region. I would like to give you some key facts about the region that we know. And when we talk about glacier changes, we normally say that we need to know the health of these glaciers. And these are the three variables which are very important for us to know the glacier changes, but also at the same time, their health. So first is glacier area, because glacier is a sort of, body of ice mass, which is confined. So we always talk about glacier area change. Glacier mass change, as we all know, that glacier is composed of snow, fern, and ice. And if the air temperatures are above 0 degrees Celsius, we can all imagine that they melt. But when you have a snowfall, they gain mass. So based on these interaction with the atmosphere, I think it's very important to know what is the glacier mass change. And the last variable is called glacier ice flow. As I told you, that a glacier somewhat is a frozen river, and they flow under the force of gravity, and there are several interactions within the body and the environment around them, so they flow. So I'm going to discuss all these variables, not only like how do they look like, how can we observe these variables, and what we know so far. So like as I mentioned, that we'll talk about how we do it. So here comes the data and techniques and what we know. So based on these observations from the scientists across the world, we know a lot. But of course, we need to know some more things, and maybe other areas of research which can come up during the QA session, and we have a room for discussion. Okay, so that is an overview of all the mountain ranges in high mountain Asia. We know that is India, Pakistan, China. And as far as the orographic representation of this region is concerned, we start from Hindu Kush, Karakoram, and Himalaya, but also these mountain ranges also exist. And these blue lines represent the major river basins in that region. So that's how the area look like when we just look from the perspective of from an orographic, like in terms of high mountains. But when we look at the Karakoram and Himalayan region, Karakoram region is located sort of like in Jammu Kashmir, Union Territory of India, and Ladakh to a great extent. But then Himalayan region can be split into three parts: Western Himalayas, Central Himalayas, and Eastern Himalayas, because Himalaya is a very long Himalayan range, and the climate is also not very much the same. So we actually, for our own ease, actually we split that Great Himalayan Range into these three sections. I mean, needless to say, but we all know why these glaciers are important. We hear from the news and stories across the world that glaciers in the Arctic, in the North Pole and South Pole are melting, have been melting very fast in the last few decades, and the meltwater from these glaciers actually contribute to sea level that we all aware of. But if we talk about the glaciers in the Indian Himalayan region, we know that the meltwater from these glaciers and snow provide fresh water for a large population living nearby. Of course, the meltwater we dam because we have to generate electricity, and also this is very important fresh water. We just don't want to waste that water so that it can go to the ocean. So we can use this water for irrigation. So the communities living in the Indian Himalayan region, they use meltwater from these snow and ice covered regions of the Himalayas. So they are very important water. They provide important water resource that we use. But at the same time, as I mentioned, the sea level rise problem is also, we are evidencing. But at the same time, we are also aware that GLOF events like glacial lake outburst floods, which happened also in a recent time in 2013 in Kedarnath, when we know that there was a lake close to a big glacier in the valley, and a lot of rain happened over a very short period of time. The lake was already full, and this lake is actually sort of part of the glacier system. So the meltwater from these glacier form these lakes. We call them proglacial lake, which is very adjacent to the glacier system. But so the meltwater is very consistent and contribute to the volume of these lakes. But if there is a landslide or big boulder, somehow fall into that lake, or what we saw in 2013, a lot of rainfall, extreme rainfall event happened over a period of 1.5 days, and so these lakes burst because we don't dam these lakes. These are naturally dammed. So we know that these interactions of these glacier systems with the landscape actually influence a lot of people in that region. So of course, glaciers are important, and that's why we need to monitor them. So a little bit about the climate, because I think it's very important part of when we try to understand glaciers. So again, that is Karakoram region and Himalayan region. So most of the rain or snowfall uh, in the subcontinent, as we know that it's happening the monsoon season, and they contribute to the major snowfall in the Himalayan region. But during winter time, this atmospheric disturbance from the westerlies actually, gave a lot of snowfall in the Karakoram region. So don't be scared of these number of plots. I would like to mention only a relative humidity that we know that during the summer monsoon, we know that from July to September, I mean, relative humidity is very, very high. But during winter season, relative humidity goes up and down, up and down. We have heard these stories that sometimes Shimla or in the Jammu Kashmir west part, we hear stories of extreme snowfall over a period of 1 or 2 days. That happens because of this stormy like westerlies, that they give extreme snowfall events over a period of 1 or 2 days. So these disturbances are not very consistent in terms of relative humidity. While in Indian summer monsoon, we know that no matter rain is happening or not, you feel very humid. So that is, different climate system actually working in that region. So in short, like Himalaya, just give you one more example. As we know that I took an image from this link. What they do is like, they give almost near real time data on precipitation. You can just go and check it out, any part of the world. So as you see, I mean, this image I took in 2019. So I checked what was happening on 24th of July 2019. And you see the entire subcontinent is influenced by summer monsoon, and also the entire Himalayas is also influenced by that. So, but the Karakoram region is largely unaffected. But what happened when you have a winter westerlies, it starts from here on 7th of February, for instance. And then after 2 days, these moisture actually travel eastward. And, at the end, like within 2 or 3 days, you have heavy snowfall events in the Western Himalaya, in the Karakoram region, where most of the Himalayan region is largely unaffected. So that's what I was saying in the series of plots. It can be seen how different atmospheric system actually working in the Karakoram and Himalayan region. Very shortly, I mean, we know Himalayas are very sacred for a lot of religions. In India, that is the terminus of Gangotri Glacier that we call Gomukh, where all the meltwater contribute to one of the largest river of the country. And we know the importance of river Ganges. Every time these melas and fairs happen, like a lot of people go and take a holy bath actually in the river systems. So in short, I can tell you glaciers are of national importance, and because they give you a reason to monitor. As I mentioned, we need to understand regional climate change, because glaciers are the natural indicators of climate change. So if you have air temperatures are rising, we can expect more ice melt, right? And when you have more ice melt, the health of the glacier declines, and that we can observe through satellite remote sensing. But of course, it's a very important water resource. I live in Roorkee. We have a canal system here, and that actually comes from river Ganges, which is also starting from the Himalayas, as we just saw. And of course, religious importance, like a lot of people travel, and they hamper their lives and influence as well. So first variable. So now we are going to learn about glacier mass change, what it is. First of all, this is sort of like a cartoon of glacier system, where you can imagine you have a bedrock, and in the bedrock, which is having a variable relief, this ice system is confined within it. So these are high elevation areas, these are low elevation areas, and this is a dynamic body of ice mass. Input is always snowfall. We saw in the Himalayas, most glaciers receive snowfall during summer monsoon, but in the Karakoram region, they have snowfall during winter time. So once this snow becomes ice because of its own weight, it densifies, it becomes ice and becomes the part of the glacier system. Then it flows under gravity, and because a lot of erosion happens because of the interaction between ice and the side and the margins, they rub the soil and rock, and erode the surface, that comes, and becomes a part of the glacier system that we call medial moraine, because and that debris actually lies on the glacier and somehow influences the interaction between atmosphere and ice that we are going to learn in this. So in general, when we just look at the glacier, it is like at higher altitude, it's always snow covered areas, because high elevation areas, we don't expect high temperatures. So snow remains snow or maybe densifies into ice. But then after snow, a little bit higher density product is firm, then it becomes ice. And then in the lower region, because of the interaction with the margins, you see most Himalayan glaciers have the debris cover, so they don't look clean. So if you go to the Himalayas, I'm not sure how many have you been to in Indian Himalayas and seen a glacier, but when you look at them, they don't look completely white. It's just because they are covered by supraglacial debris that comes with the interaction. And of course, a lot of landslide happens in that region that also falls onto the glacier system. And this is actually very dynamic. So all the debris comes at the lower part of the glacier. So that is like, yeah. So the concept of when we observe glacier mass change from space, like from satellite remote sensing, what we do is we map the topography at a particular time. So this is green line, which is shown that, okay, the height of the glacier is at T1 is H1, for instance. But after a few years, maybe 5 years or 6 years later, at time T2, we say the height has changed because the ice has melted. So when ice melts, the thickness of ice actually reduces. That we can also imagine if you take an ice cube from our refrigerator and put it in a bowl. After a while, what we see, a lot of water, because ice melts, but the thickness of ice cube also reduces. The same concept. So now you know that how we know what is glacier elevation and mass change. Now we need to know how we can observe them. So like one of the techniques is differential GPS. What we have to establish a base station somewhere on the rocky terrain, and the rover, we have to just walk on the glacier so that we can estimate X, Y, and Z or several locations. So after a few years, we can go and walk on the same terrain, and we can say, okay, the glacier has reduced its elevation, and then we can transform into mass change. So that is one of the technique. But of course, you can, as I mentioned, glaciers are often located in harsh conditions, and it takes a lot of human efforts, and you need a lot of resources and manpower, and it is not often easy to reach glaciers and observe them every month or every year, for instance. And that's why several space agencies across the world have launched satellites so that we can monitor them even though we cannot reach. So first mission is called satellite-based laser altimetry. So what they do, as you can see in the satellite, they throw green photons that actually reflects back from the surface of Earth, and that's what you see, like the footprints. This is not an imaging satellite, so we don't take images in satellite laser altimetry. We just throw laser beam. It is reflected from the Earth's surface, and that's how we estimate the elevation. And over a period of time, we just estimate elevation change. So there was a mission by NASA. It's called ISET-1, which lasted for 5 years. And now they launched a new mission in 2018. It's called ISET-2. It is an ongoing mission, so it's taking data all over the world, and it's a very important mission. So based on this ISET-1, this is study by Andres Kebe and others, published in Nature. What they did is they accumulate all these elevation information and apply some mathematics. They interpolate and also average out over a period of time how much, this in every pixel, for instance, or a bin, you can say, what is the trend in elevation? And based on that, they calculate a surface elevation change. And when we say in Karakoram Himalaya, you see all the red dots, it means glaciers in that region are actually losing mass faster than other region. While in Karakoram, we know that glaciers are actually not losing mass, even they are gaining mass. What we don't see in the entire Himalayan region. So entire Himalayan region, is losing mass, of course, with different rates. But in Karakoram, the glaciers in general are gaining mass. So that's why we have started calling this uh, Karakoram anomaly. So this is an anomalous behavior because we know that in the recent decades, the glaciers across the world are losing mass, but in that region, they are not. Then comes a second technology uh, that we call satellite-based uh, photo photogrammetry. What we do is like, and this is based on imaging system. So what we do is like we need to have two images in a visible band and a slightly different angle, and both these images should have an overlap, and based on that we can generate the topography of the region. And once you have the topography, after a repeat pass, you can estimate glacier surface elevation change. What we see, I think, yeah. So what we see here is basically based on Aster mission. Aster mission is also by NASA. And so what they do is like it was launched in 2000. It's still going on. And this study, what they do is like they accumulate all the digital elevation model in a specific area. For instance, we are talking about this. So for a pixel, for a certain area, they say how many elevation points are available. And based on this algorithm, we say, okay, there's a seasonal change that we can monitor. But from this, we can say what is the long-term trend. So based on this information and this algorithm, what they say is like over the period of 15 years, the glaciers are losing mass or not. So they give you one value for a pixel for 15 years. So based on that, they extended the previous study and they say, okay, not only the Karakoram and Himalayan region, but other regions in high mountain Asia. And they found actually more or less the same results in Karakoram Himalaya, where this region slightly extending to the Kunlun mountains here, the glaciers are actually gaining mass, while the entire Himalayan region, this is Laol, Spiti, and Uttarakhand, and so on. I mean, most of the region, like almost all the region in the Himalaya, is actually losing mass. Then comes a radar mission. So but we need to know why need to build a new technology if there are two other technologies existing. Is because first is altimetry. So every technology has some advantages and disadvantages. So with satellite altimetry, this is not an imaging system, so we cannot take images. So all the observations are very sparse. So you have to apply some averaging technique. You have to do some interpolation, and that's how you estimate glacier elevation and mass change. But what happens in the photogrammetry, they are based on imaging system in a visible band. And what happens, in the Himalayan region, for instance, after 2 p.m., you don't have, you have clouds. And in Europe, for instance, you have during winter time very limited solar radiation. So that system requires incoming solar radiation. You need to have a sunlight, otherwise it won't work, and you don't have any data. That's why space agencies have built radar systems on board these space, because radar can see through clouds and you can acquire data in the day or night time. And why is because it has its own source of illumination. So it sends its own electromagnetic signal that interacts with the surface and goes back to the glacier, to the satellite. And that's how, but you have to apply some technology, and the technology name is SAR interferometry, because here we are talking about the phase information, like phase of electromagnetic signal. And after a period of time, if there is a change in the topography, this phase will change, and based on the phase difference, we can estimate, elevation change and so on. My group at University of Erlangen, Germany, actually, applied 2 radar missions. One is SRTM. This is Shuttle Radar Topographic Mission. It was an 11 days mission by NASA, where they have, now we have a free open source near global digital elevation model across the world. But this mission was launched, as I mentioned in the previous slide, by German Aerospace Center, which is a German space agency. And what they do is, you have to, they take two images. As you can see, this is a constellation of 2 satellites. So these 2 satellites take 2 images simultaneously. And based on these 2 images, you can generate a digital elevation model. And that's how we did. So in 2000, we have SRTM DM, which is openly available for everybody. And this we generated by ourselves. So we have 2 digital elevation model, one in 2000 and one in 2012, 14, and 16. We subtract and we get like what happened like in the last 15 years. And we got like more or less the same story with one more independent observation. I think that is more important in science, that I think it's good that we conclude the same thing, but if we apply different tools, then I think the reliability of your observation increase. So what we saw also, like in entire Himalayan region, is losing mass much faster than the glaciers in the Karakoram. So I just focus here because I started my PhD on these topics, and then afterwards, after I left, Philip Mal joined as a new PhD student in the group, and used the same scripts, improved them, and extended for the entire region in High Mountain Asia. So I just focus what I did in that region. Just excuse me. So as you can see, these are glaciers. Jammu and Kashmir West, and this is now Ladakh region. So, and these are small glaciers. These are not actually small. They look small, but they're not. But we are talking about 1,000 glaciers in that region, also 1,000 glaciers in that region. We use 2 digital elevation model, one in 2000 and one in 2012 that I generated. And when I subtract them, you see, all the red areas. So all the red areas means, the ice is melting, and that's why you have negative elevation change. But of course, in the higher accumulation area, higher altitudes, I mean, ice is not melting as much as in the downstream. So that's why you see sort of some green points as well. What happens in Ladakh region, you see some significant negative elevation change, and these negative elevation change and the positive elevation change as well. So I think that is how we identify what is the rate of ice melt in these regions. I also did one study in Lahaul Spiti, which is in Himachal Pradesh. And as you can see, again, approximately 1,100 glacier, even the small ones. And these observations are spatially detailed. Why it happens is because we worked on radar remote sensing, and we don't miss any information due to any cloud cover, for instance. But it can see through cloud, so we don't miss any part of the glacier, and that's why you see very detailed observations. This is the largest glacier in that region, called Bada Shigri Glacier. And I zoom in it a little bit, and you see that because of supraglacial lakes, as we can imagine, water bodies absorb more solar radiation and the heat and that sustains the energy for a longer time, that actually enhances the ice melt beneath. So that is the reason that at these locations you have significant negative elevation change. But at the same time, um, these light orange areas is because of the debris. And why it happens? Because of the debris, they work as an insulator, because they somehow restrict the solar radiation to reach the ice beneath. And that's why at the same location where the clean ice is actually losing, it is melting faster than the ice beneath the debris cover. So these are the things, if you have detailed observations like that, you can do some more studies of that kind. So in general, what I found is so I told you in Himalaya, I studied around 2,400 glaciers, and I have observations of every single glacier. And so what I did, I plotted the mean. I plotted the mean elevation change rate of all the glaciers in the Himalaya. And what I found is that that peak or the cluster is away from zero line. So zero means the glaciers are not losing, the glaciers are not gaining. So they are in balance, right? But in Karakoram, what I see, the cluster is towards zero. But of course, a lot of glaciers are losing mass there as well. So when we say the anomalous behavior of glaciers in the Karakoram, we are not saying that every single glacier is gaining mass there. All we are saying is, in general, on an average, they are close to balance, or they are less negative than Himalayas. But yes, as you can see, a lot of glaciers in Karakoram is actually also losing mass. But of course, this is towards zero line, which means, okay, the rate of uh, mass change in the Himalaya is faster than in Karakoram. So now we move on to what I also did in my study, because I think it's very important that we know that what we know. So so I got these two observations in hold on. Okay. Yeah. So in that picture, you see, I included a number of studies which happened in the Himalaya and Karakoram region, and also found that in general. So these are the two observations from our studies. So JK West is like Jammu and Kashmir now, and JK East is Ladakh region. That is Himalaya, and that is the Karakoram region. And what I found that in the Himalayas, the glaciers are in general, have elevation change rate is much faster than glaciers in Karakoram. So these are the glaciers region in Karakoram, and it's just not based on my study or our studies. I have included a number of significant studies and found the same thing. So now from various evidence and various ways to show our observations, we can say that glaciers in the Himalayan region are actually losing mass much faster than glaciers in the Karakoram. So that there is a regional heterogeneity. But as I mentioned earlier, so we have a clear understanding of regional heterogeneity, not from our study, but also several studies on the topic. But we can just go beyond, because we have spatially detailed observation. We have observation everywhere on the glacier. Can we know something more about the trend on glacier level? So that's what we are going to see here. So that is one of the glacier in the Himalaya, and as you can imagine, because of the debris cover, you don't see any clean ice. So you see some clean ice here, and that's where you have all the river system originates, like Gomukh for instance, this is not a Gangotri glacier, but the glacier end is sort of like every glacier system has this like mouth shaped, what we call gomuk in case of Gangotri glacier. So and that's where all the melt water from the catchment, due to snow melt and ice melt, and also the water body system, they lose water and they all go all the way to the down valleys and contribute to all the major river systems in the Himalayan Karakoram region. So that is how a typical glacier in the Himalayas look like. So you have these margins, steep slopes, and you see landslides and eroding surface. And glacier is covered by debris. You have supraglacial lakes and ice cliffs because of the dynamics, because glacier is not a stationary body, it's moving, and that's why these happen. So when I apply the glacier elevation change, we find some patterns. So in that particular area, we understand the ice has melted a lot, that you can imagine. In that vicinity, we can say because of the moving, it looks like the glacier is the glacier is gaining elevation, and this is there's a reduction in glacier elevation. It happens because of the dynamics. So some ice is transported down the valley, but also if we see some red patchy area here, we see that it is because of lake and some hot spots of these kind, of course, because of the ice dynamics too. But at the same time, what we found, there's a big debris cover. It is thick enough to insulate the ice beneath, and that's why ice is not melting fast, and that's why we start to see that okay, the glaciers in that region is not reducing surface elevation en masse. What happens in that case where we see a patch of ice is mixed with debris, and this debris cover is not thick enough, and that's why it actually absorbs more solar radiation, less albedo, and that's why it triggers ice melting, and that's why we see negative elevation change. And of course, also because of lake, as I mentioned, these water bodies always they absorb solar radiation, and energy flux is changed in that region. But of course, like as I mentioned, that I studied 3,500 glaciers. So I cannot do this exercise for all the glaciers in the Himalayas and Karakoram. I have to find a way to understand whether there is an influence of supraglacial debris or not, right? So what I did is I wrote a piece of code and applied to all the big glaciers in that region, and I found various pattern of surface elevation change. So ideally, I found one set of glaciers where, like, in that plot, x-axis is the elevation, this altitude distribution of the glacier. So this glacier is like the lower end is 4,200 meters and goes up to 6,000 meters and so on. These bars actually indicate the glacier area in that particular pin. For instance, at 5,250, this glacier has, more glacier area, or the most glacier area is of that particular glacier is located at 5,200 meters. So maybe it broadens a little bit when we go upstream. And what do we mean by this black part? So that part of the glacier is covered by debris. So that's what it means. So what we found that, okay, this is almost a clean glacier, sort of, because the debris cover is not everywhere and it's not very influencing factor. And we see elevation change. So these red dots actually indicate the surface elevation change. And you see at the lowest altitude, you have highest surface elevation change. And that we expect, because at the lowest altitude, we see higher air temperature that contributes to glacier ice melt, and that's why we see significant surface elevation change, which reduces when we go upstream. So that is obvious. Like the glaciers should ideally behave like that. But this set of glacier, where we see these are highly debris covered glacier, and entire area of these catchments of these bins are covered by debris, which means you know the debris cover is an influencing factor in that particular case. So you see highest surface elevation change when there's no influence of supraglacial debris. So it means this happens because of the insulation effect of debris. And afterwards, of course, the glacier behave in a normal way, because this is now we're talking about clean ice. The third type of glacier where we also see this is also very highly debris covered glacier, but we see the similar pattern like this. And what is happening here? Because the debris should insulate the ice here as well, but it's not. So then we started understanding what is really happening. So what you see in the previous picture, when you have debris cover at this altitude, for instance, it is a game between two effects. So one is the game that the debris cover insulating the ice beneath. So it is protecting the ice, but at the same time, at the same altitude, this is actually enhancing the ice melt. So it's a game, and whoever wins, that is what we get in these plots. So what we saw that these type of glaciers, we see a lot of lakes and ice cliffs that contribute to the ice melt, and they always win. So that is, we need to understand. So so far, what we have learned is like we have a regional heterogeneity, a regional understanding of glacier elevation and mass changes. Then we narrow down in a sub-region and found what is happening on a glacial level and the influence of supraglacial debris and lakes and water bodies and so on. So when we talk about why the glaciers are changing, it's also because of the climate, because of the interaction with air temperature and snowfall events. But at the same time, the glacier system itself contribute a lot to their own health, and it happens. And we can simply say, if a glacier is a debris covered glacier, if they are showing insulating effects, they are delaying the climate signal, right? Because if there is a fluctuation in air temperature, right? So the glacier melt should enhance, but they are not, because of the debris cover, they always insulate the ice beneath. So that is the reason why we say, okay, this debris cover delays the climatic signal, what we can understand from these glacier changes. But at the same time, water body and thin debris cover, they speeds up the climate signal, because even though there is slight change in air temperature, they can absorb a lot of radiation, and energy flux in that region changes, and they enhance ice melt. And that we understand, okay, look, okay, there's a slight change, but there's significant change over there. So that sometimes contributes and also speeds up the climatic signal. So all these studies, including my study, we talk about what happened in the last 1.5 decade. But we are also interested to know, are these changes happening or very consistent in the last 1.5 decade, or is it something happening like all the time? So this study actually identifies that ice loss across the Himalayas over the past 40 years actually accelerated. So they actually did a study on 2 different times. So in 1975 to 2000, and the other time period is 2000 to 2016. You might ask, what sort of data was available in 1970s? So as you know, after Second World War, US and Russia both launched some spy missions, and they took a lot of images across the world. And these images were classified in the late 90s or early 90s. And they were also stereo images that we just studied, satellite photogrammetry. And so they applied digital photogrammetry and estimated digital elevation model in 1970s, and in 2000 you have SRTM already. So and they subtracted to get the surface elevation change, and they convert glacier surface elevation change to glacier mass change. And in 2016, we have a plenty of missions, right? So in 2000, again, SRTM, in 2016, they used, I guess, Astra data. And what they found that across the Himalayas, the rate of change, as you can see, these are the latitudes, and right from 77 to 91, 92. I mean, the rate of mass change has doubled in some cases, but overall, accelerated. So what we can also see in the recent times, because of the climate change, and the glaciers are losing much faster, and yeah, it is a sign. So from this part of my talk, I want to indicate three different things: that there is a regional heterogeneity, which means positive or near stable glacier mass change in the Karakoram compared to the Himalayas. We saw that Himalayan glaciers are losing much faster than glaciers in Karakoram. So glaciers so that is, that we can just skip, because I'm going to show some more results in my upcoming presentation. And remote sensing data of very large number of glaciers indicate the role of debris cover, supraglacial lakes, and ice cliffs. So sometimes we do these regional studies, but we have to look very closely and also try to understand what are the system inherent factors that contribute to these changes, right? So we understood that both insulation and enhancing effects that play around at a certain altitude, and that plays an important role in these glacier changes. So I think these are the two key messages, and there are plenty of satellite missions which have been there and which are operational, and some of them are upcoming. So that's you can make use of them to study glacier surface elevation and mass changes, and can monitor. This we can take later on in the discussion. Now we can move on to the other part of my presentation, that is glacier area change. Okay, so when we talk about glacier area, so I showed you one example. This is a very confined body of ice mass due to the topography in that region. So we can map the glacier area, and glaciers retreat, as you see in case of Gangotri Glacier. So if you would have if you had born in 1780 from Gangotri Mandir, you didn't have to travel all the way here. Like in 2001, I suppose in 2020, Glacier Terminus or the Gomukh is located somewhere here. And as you can see the scale, this is 1, 2, 3, 4, like, so if you were born in 1780s, you wouldn't have to travel 4 kilometers more that you have to do today. And it happens because the glaciers retreat, right? As you can also see in this image, in 1921, the glacier from higher altitude to the lower altitude is over there. And somebody took I think stood at the same location and took the imagery of that particular landscape. They found that there is now a proglacial lake, and the glacier retreated far inland. So glaciers retreat, and they tell you a lot about the glacier health as well. But I told glaciers in the Karakoram are also surge type. And surge type glacier, I show you how they look like. So you focus on my pointer here and see this glacier is advancing, and then it slightly merges into the main glacier here. See, that becomes a part of the main glacier. And also this glacier, if you just look at, so it is advancing, and also becomes a part. This also advancing a small glacier and become the part of this glacier. So these glaciers, like, they are moving, as I told you. So what the author did in this paper is basically, accumulating all the image in the last 15 to 20 years, and create that sort of GIF image where we can see the movement of these glaciers. So every part of the glacier is moving. We see the changes in the landscape, but I just want you to, just have a focus on these glaciers, which rapidly move over a period of very short period of time, and they are called surge type glacier. So it's a sort of event very common in Karakoram, and they actually hamper uh, imagine if this glacier advance all of a sudden, and there's a river system, it can block the river, and there might be a new lake that is formed, and after a period of time, when this lake outburst, it can create disaster in the valley. So these phenomena we also need to understand. So these glaciers, when they surge, they also advance. So all we have to do is we have to map the boundary of these glaciers, because that gives you glacier area. And if the glacier area is reducing, we can say the glaciers are shrinking. And if the glaciers are shrinking, it means the health of this glacier is declining. But yeah, as I told you, most of the glaciers, or I think almost every single glacier in the Himalaya, is debris covered, and we don't know, like, where they are located. So suppose this is a rock glacier, and as you can imagine, the the terrain here and here look the same, and we don't see very clean ice. But because ice is beneath this debris, and so how we do it? Because if you take an optical image of this kind, we cannot distinguish. I mean, here now okay, that's how the glacier look like, because I tell you. But if I just give you this image without these outlines, you can't say that the glacier is going this way or this way, and we cannot map the glacier. If we cannot map the glacier, then we cannot estimate glacier area. So what they have done in that particular case, it's a very small glacier, maybe 1 kilometer long. So what they did is they established a base here, and they took the rover, and somebody has to scratch the debris and feel the ice, and they walk all the way, and they found the glacier area. But as you can imagine, we have thousands of glaciers across the world, and this is not a feasible way of mapping the glacier boundary. Of course, then we have to rely on remote sensing, and the first technique is called optical remote sensing. But here, you can fairly say, okay, look, this is a snow-covered ice. Maybe there's a glacier here, but I'm not sure, like, where the glacier ends. And that's how it looks like. So glacier outlines, and now but we don't. I mean, we can't say here that the glacier is over there or over here. So, but of course, we have to make use of that information. If you're working on a very small area, then I think it might be feasible. But of course, there will be errors, because human intervention has some limitations, and that's what we found, that in optical remote sensing, uh, the spectral response of the rocky terrain and the glacier remain the same, and it's not very easy and straightforward technique to map the glacier. Then comes, some people have tried to use thermal remote sensing data, which means you have the information of surface temperature, And the basic philosophy here is rocky terrain is warmer than debris covered ice, is because if the debris is thin enough, there's an exchange with the ice beneath, and they are cooler than the rocky terrain nearby, and that's what people tried, and they found, okay, they can map the glacier surface to some extent, but not entirely, because when we have a thick debris cover, which means the cooler ice cannot interact with the entire column of supraglacial debris. And that's why at the top of the surface, you might see the similar surface temperature as of rocky terrain. So that's why this technology, it works to some extent, but it's not working absolutely fine. Then comes a new technology called INSAR coherence. What they do is basically, it's based on radar remote sensing. So it needs two images, and you have to apply SAR interferometry. It's a technology. If you have a question in the discussion, we can discuss these topics. But just very briefly, you have two images like over a period of time. And I told you, no matter if the glacier it is a debris cover or snow cover, every glacier in the world moves, maybe slightly, but moves every single day. So they are not stationary. They always flow under the force of gravity. And that is sort of information we use in radar remote sensing, where we say, okay, we map the phase at one date, and after a period of time, we use we use the phase again, and we apply the phase difference and see, whether we can estimate the ice velocity, or this parameter is called INSAR coherence. The values of INSAR coherence, it's a product of SAR interferometry. When you apply SAR interferometry of two images, where you have to first register two images, then you have to create interferogram, which is the phase difference information, and from there we can generate coherence. And coherence values lies from 0 to 1. 0 means the surface has changed a lot, or the surface has changed significantly over a period of time, so of these images. And 1 means, the surface is stable enough, and that is the information we need, because we know all the rocky terrain nearby, they are stable, and that's why they give you very high value of INSAR coherence, around 0.8, 0.9 or something. But the glacier terrain, as you can see, it's moving slightly, but it's moving. And when it moves, we can apply this information. We see the coherence value over glacier is not high enough. So it's around 0.3 or 0.4, and that information we can use. So I see in that particular glacier, clean ice is everywhere. We can simply map that glacier, but the glacier is actually extending towards the lower altitude here. There are a lot of supraglacial lakes and so on, but this is underlying ice which is there, and we need to map, which is still a part of the glacier, and that we could do in INSAR coherence. So with INSAR coherence, what we it's not dependent on solar radiation. In case of optical remote sensing, it can see through clouds and day and night. So we have observation all the time. And if we can apply the phase information, we can map the glacier area at any point of time. So based on these techniques, there have been several studies which map glacier frontal changes, because normally the glacier shrinks from the front, not at the top. They reduce ice, but as far as the area is concerned, they always change from the front. And what we found so far is basically the Himalayan glaciers are actually retreating more as compared to glacier in Karakoram. That's similar story. In Karakoram, we know that glaciers are stable. In Himalaya, they are losing much much faster. In the Himalaya, what we see, if they are losing mass, it also have an implication on the frontal stages, because not enough mass is withdrawn from upper region to lower region, because they are losing mass, and that's why when you don't have a supply system from upper altitude to lower altitude, and the glaciers, they cannot extend, so they will retreat, and that's what the signal we are here across the Himalaya. What we see is glaciers are retreating much faster as compared to glaciers in Karakoram. This is a nice study by my colleague Mirani Rankal in 2014. We were doing PhD together, and when she was preparing that figure, when I first saw it in 2012 or 13, it was very fascinating and very easy to understand that in the Karakoram, this is a lot of glacier in central Karakoram. They have surge type glacier. So like the glacier which I just showed you, where they're advancing and merge into the main branch. Some glaciers are advancing, like some few, like 1 or 2 or 3, 4 glaciers. So they just don't move very rapidly. They just move slightly over a period of time, and they advance as well. Retreating glacier. So glacier in the western Karakoram, they retreat, like what we see in case of Gangotri glacier. And a lot of glaciers are stable. They are just not retreating and advancing, and that happens in the over a period of 36 years. So as you can see from here, that most of the glaciers in Karakoram are either surge type, which means they are expanding over a period of time, a very short period of time, but they are stable. And once they are stable, which means there's a constant supply system from snowfall and also to the lower altitude, so that they are in balance. They are always in balance. So that is also one implication on the glacier. So I call it stay home messages because of the COVID era, not take home messages, because all staying at home. So what we saw is there are various techniques available, but should be carefully applied for debris cover glacier. So if you want to map the glaciers in the Himalayas, I would recommend you should always see whether this is you can easily see the front or not, because there are some signs. There might be some river systems which are originating from the glacier, and then you can see, okay, that is the front. But if you don't want to work on this, by yourself, and you want to apply a semi-automatic or fully automatic technique, I would rather say that you should really apply radar remote sensing, because the data is free, and we can make use of it. So what we learn is, like, Himalayan glaciers are retreating across the Himalaya, not advancing at all, but many glaciers in Karakoram surge type and stabilize, most of the glaciers. So now we move on to the last section of my presentation. So, again, I would like to show that picture, that when we talk about glacier movement, that's like when you go to any Himalayan valley and evidence any glacier, you won't, you can't see the movement, even though, like Himalayan glaciers are not moving very fast. They are like centimeter per day, or like very slightly. So you cannot discern. But even though if you go to glaciers in Greenland or in Antarctica, for instance, these glaciers move very fast, sometimes 40-45 kilometers, 40-45 meters per day. But even though when you stand or, seeing somewhere, you cannot discern that they are moving, because it's a very slow rate, actually, 45 meters over a period of 1 day. So you have to see that glacier throughout the day, which you cannot do, right? So again, the satellite remote sensing, if you sequence all the images, you can see these patterns. Like they are moving, these movements this glacier is becoming part of that glacier, and that it merges and advancing significantly. So they are moving from upper altitude to lower altitude. Also, look at this glacier. You don't see any signs of movement, but then it start to advance and some cloud cover. But now they see it's advancing. It's even started from here, very high altitude, and it goes all the way to here. Amazing. What we mean. So again, why glacier ice has to flow? Because of the gravitation. This is a driving force, and we cannot stop. I mean, gravitation is the most important part. If we jump and so we have to fall on the surface of Earth. So I think from higher altitude to lower altitude, these glaciers flow. But since I told you that glacier ice is lying on the surface of bedrock. Recall the first image of glacier I showed, the cartoon, which actually, the glacier body is lying on the bedrock, and it has margins, for instance. And imagine at the bottom of ice, there's an interaction between the bedrock and ice, and it has some friction. So the glacier flow is restricted due to that friction force, and we call that basal drag. And at the same time, also, because of the margin has the same material, so frictional force over there as well. So when the glacier is moving in that direction, they stop the glacier movement. So we call that lateral drag. So this is, I mean, gravitation is a driving force, but is basal drag and lateral drag are actually, are stress are not the driving forces. They are actually stopping forces, I would say. And since glacier body is a long body of ice mass, right? So you have a lot of compressional and extensional stresses. So like when ice up is pushing in stress and extension and compression are happening. So some are contributing to the flow, some are actually working against the flow. There are 3 or 4 mechanisms that happens. But of course, that is the basic physics of glacier. What I would like to emphasize here, when we work on any data, any satellite data, we always need to work on images. So you can imagine this is the first image, and this is the second image over a period of time. And what we see is we have to find features that move over a period of time. So normally these techniques are called feature tracking, and where we have to define a bigger window in a second image, and a smaller window that we want to look at where it is located in that particular. So this is a bigger window, this is a small window, and at that particular area where we match that feature, and based on that we can say, okay, maybe that so I think this is highlighted here. So if that feature moves in that particular direction over a period of time, that is what we call the ice velocity, the displacement that we map using a normalized cross correlation function. So for every matching, we calculate this function, and the maximum of this function gives you the most similarity, right? And when you have the most similarity, like value of 0.8, for instance, we are more confident that, okay, that particular feature is located in both the images, and that moved in that certain direction. And based on that information, we calculate the ice velocity from space. Some results from my side. I mean, this we can skip. Or maybe we can take this one just to understand. So this is like a mountain glacier in Alaska, one of my PhD topics. So this is a glacier, this is ocean, and at different altitudes, I estimate the velocity. So like right from green, it is located here. And on x-axis, we see right from June 2011 to June 2016. It's a 5-year information that we see. And I think you should focus on this part only, where y-axis is the velocity, meter per day, right from 0 to 16. So what I saw that, okay, at higher altitude, the glaciers are not moving very fast, and they are moving around 2 meters per day, more or less. But like the glacier at the front, close to the ocean, because there's an interaction between ocean and ice and also atmosphere. We always call ocean, ice, atmosphere. What we see, there is a seasonality. So like if you start from June, July, August, and February, March, and so on. So they have a speed up period in late winter, early summer, and then in the late summer, the velocity goes down, and then speed up again the next year, then slow down, up and down, and so on. And I also did is the area change, which is like glacier area change that we just saw. There's also fluctuation in the glacier area. So sometimes these are ocean terminating glacier, and there's no ocean in the Himalaya. So there's no ocean terminating glacier in the Himalaya. They all terminate to the land or lake, because there are some new lakes that have formed. So there's an interaction between water and ice. But in general, what I have found, if we just, we combine all other information, in that particular case, we apply what is the minimum temperature and maximum temperature. We can say this is springtime. So this is where we have the minimum and maximum temperature is above 0 degree, and these are winter times. And then you go, so this is late winter, and spring arrives, and then you have extreme summers, and then you have autumn, and then winter, and so on. So that's how we understand. If you have in the springtime, if you have more melted water that gets into the system and somehow changes the subglacial hydrology. What I mean by that, I told you that there's a basalt drag, there's a friction force at the bottom of ice because of the interaction between ice and the bedrock. But the water during spring that gets into the system, the water reaches the bottom, so right. And when imagine there's a water between ice and the bedrock, the friction force is reduced. So that's why ice flows very fast. So that's what, we from these observations, we can infer that this is happening because of that. So we can hypothesize based on this, based on these observations. So we don't have to go there and dig 300 meters of ice and need to find the evidence of this water. Of course, some people have done it, and we have to do it, but at 1 or 2 locations we have to do it. Otherwise, for most location, if we find the same signal, we can just make a similar story of this kind. So in the Himalayas, what we understood, like this is similar map what we saw in glacier elevation change, where the Karakoram is having very positive elevation change. This study actually identified or estimated glacier velocities in that region, and what they found that glacier in the 21st century slow down. I mean, the ice velocities of these glaciers have actually declined. So they accelerated in the recent times. So as I told you that story, if you have if the glacier gains a lot of mass, that mass has a gravitational force and that flow. So when you have flow, you have high velocity and the glacier also advance. But if we know that in the 21st centuries, in the 21st century, the glaciers are losing mass and they are and their surface elevation change is declining. So there's not enough mass to travel from upper altitude to lower altitude, and that is the link that study finds that 21st century glacier slowdown driven by mass loss in high mountain Asia. So because of the glaciers are actually losing mass, so they will slow down. So that's how we know. But of course, in the Karakoram, we know the velocity change is positive. So there actually the velocity is increasing. So they have accelerated in the 21st century because they gained a lot of mass. A little bit about from Greenland, I think we can wind up afterwards. So, and why Greenland? Because I have worked in Greenland, and once we understand glacier system as a whole, that knowledge we can also use in the Himalayas as well. And of course, you know, I'm not sure, like some of you might be interested in studying ice and other phenomena in the polar regions as well. So so why not? Why to limit yourself to the Indian Himalayan region, for instance? So that's what we see from space. These are small lakes over ice. These are freshwater lakes and not contaminated at all. And I mean, see, they're so good. And ground reality, of course, when we take a picture, they all look like that, like similar. And this study identified the supraglacial lakes on the Greenland ice sheet advance inland under warming climate. So we have a story that these lakes across the world are increasing both in numbers and size. So if there is an existing lake, the lake area is expanding in the recent times, or they are increasing. But if there are no lakes, I mean, new lakes are forming because of the climate change. So this is one of the region in Greenland, and I focus on that particular lake and see what happens. So on 18th of June 2017, you don't see any sign of this lake because lake water is frozen, and you know, and the surface is also frozen, so not enough signs of water. But on 20th of July, I mean, the water on this lake exposes. I mean, because the air temperatures rose, and that's why you see the full extent of this lake. This is an optical image, so that is more or less a real world. That is ocean. These are icebergs that we always keep on hearing from the news, and these are radar images. That's why you see black and white image. But as radar, imagine in the polar region, you cannot have optical images without any cloud cover information. So there's a lot of radar images which are useful. So we say the full extent of this lake on 28th of July and 3rd of August. Still, I mean, the lake has a full extent, but on 9th of August, for instance, after a week, after 6 days, I mean, the glacier starts to drain. This glacial lake starts to drain. And on 15th of August 2017, you know, the glacial water disappears. So that water goes into the base of the glacier and it smashes and also speed up the ice and goes into the ocean. So that's why a lot of glaciers are losing water into that ocean. And imagine, like, you know, if you have a question, like, why are we studying glaciers in Greenland? But you need to know. Yeah, but you need to know that this fresh water from Greenland ice sheet to the ocean, they come to the equator, and from equator, warm water goes to the polar region. And that's how we have a lot of climate system in this world. And we have some evidences that this water does not stay there. And sometimes in South India, we have extreme rainfall events in September, October, even after the monsoon, you know, because the monsoon returns, so this water sort of goes from there to there through the climate system. So I think that actually directly or indirectly hampers our daily life, and I think we should contribute to do a better understanding of these glacier systems and to see how much water they influx to the oceans. So as you can see, when you have a lake drainage event, in this plot, you have the weeks of 2017, right from 0 to 52. And these are the ice velocities. And you see the acceleration in the seasonal acceleration. But because of the drainage event, which is like lake drainage event, you have all of a sudden speed up and slow down events. So what happens is when the extra water goes into the base, it actually it increases the water pressure at the base and push ice in a way so that you have a speed up event of like for a very short period of time. When the water releases, the pressure reduces and the velocity, the glacier slow down. And that's sort of signal we get here, like slow down event, but then again recover afterwards. So that's what I explained. Since I have been using a radar mission, I would like to emphasize that now I think most of the space agencies have realized the importance of radar mission. So in the 90s, you had only 3 or 4 missions, but now after 2000, you see a bunch of satellite missions operating with different radar frequencies, and yeah. And I want to emphasize the upcoming mission. It is located in 2020, 2022, but because of the COVID, it is delayed now. So it is early 2023. That is a joint NASA-ISRO SAR mission. It will be of 2 radar frequency. S-band frequency will be operating in India and the nearby region, also in Antarctica. But L-band data from NASA will be like a global mission. And the data will be open source and free for everybody, for us, so that we can use for any application. So that is the strategy. As you can see, the SAR mission is S-band is operating here. Otherwise, L-band is over like the entire globe. So now 2020, 2023. So stay home messages from this part of my presentation is like optical and radar remote sensing data may capture glacier ice velocities. As you say, you need two images, and the features should be visible on your images so that we can track, and the technology is called feature tracking. Of course, there are some other techniques as well, which we can discuss during the discussion. And I say many opportunities of using space-bound radar data, as you just see, and future is bright. NISA mission is coming. So with this, I would like to end my presentation, and thank you very much for being there and for listening to my talk. Thank you so much.
Thank you so much, sir. This is Dr. Alora from Shivnadar University, and the presentation was really nice and very insightful. Sir, voice is okay. It's my pleasure. So with this, I'd like to request the audience, the participants, to ask the question if they have any, and they can also write their question in the chat box so that we can read and you can address their questions. So
sure.
Yeah. Participants, please unmute yourselves so that you can ask your questions. We can wait a couple of minutes because actually it takes time to type the question, and
that's
so
right.
that, yeah, so we can wait for a couple of minutes.
I understand this is a lot to take in, and if you are not working in that direction of research, but if you you might have questions regarding how to access these images, whether these images are free or not. Yes, of course, there are few missions from European Space Agency and NASA. They're absolutely free and it is available to everybody. But of course, there are some missions like the Tandem-X, which I showed and also used in my PhD. You have to write some science proposals, and then if your proposal is accepted, I mean these images are available to you free as well. And when we say how to access the images, then the next question comes how to access these images as well. So I think we can take for our first question.
Yes, sir. Yes, sir.
Maybe I can read out how datasets for crop classification can be obtained. So crop classification, I mean, it might be based on some vegetation index. So I would say you can either use remote sensing images from several space agencies. I give you some. NASA, for instance, European Space Agency, Indian Remote Sensing Mission, or hyperspectral images. Yeah, that's right. So you have to understand the multispectral image missions are free, a lot of them now, but not the hyperspectral images. So you have to always find whether for your study area, is there any hyperspectral image? Is there any hyperspectral mission going on or not? So, and I don't know. I mean, your question is like how dataset for crop classification can be obtained. I mean, some people can use radar remote sensing data also to understand the growth of the crop. But if you want to classify different crops, I think you have to rely on hyperspectral images. But you have to check like what is your study period and location, and based on that you can just obtain them. I mean, for India, there's no ongoing hyperspectral mission that we can have access to.
Is there any more question from the audience side?
I think hand raised by the Athya.
Can you please go ahead? Please.
Shirshak Gurung.
Yeah.
Yeah. Yeah, Session, you
Okay,
can.
sir, good afternoon, sir.
Major.
Sir, actually, lately, sir, there's been a lot of talk in terms of glacial lake outburst floods, sir, GLOF, and it really got me interested. But today, again, you talked about something new, sir. You talked about debris covered glaciers. So first off, I wanted to really go into this research and have an inventory made. But then, sir, my first question is how, the influence of debris-covered glaciers to GLOF, sir. And second is, sir, should we use in order to go for this GLOF study, sir?
Yeah, I mean, if you are interested, I think you should go for it. Yes, I understood your second question. So I would like to answer the second question first. The thing is, like, you are interested to study GLOF events. I think that is very interesting area of research. In the Himalayas, recent studies have highlighted that glacial lakes in the Himalayas are also increasing. So they are also increasing in numbers and also their sizes. So this is not a good news. But for scientists, I think that is very interesting to study the interaction between these glacial lakes and the glaciers. So if you are interested, you should go for it for sure, because they actually, they influence a lot about the water discharge in the valleys. Your first question is the debris covered glaciers, right? So what would you like to know about this?
So do they contribute to GLOF? Or do they contribute to disasters?
They might. Yeah, they might, but it's not specifically. So why does GLOF happen? So the glacial lake burst. So why they burst? It could be because they are naturally dammed, right? So we human beings don't go in the valleys and build a dam there. So they and these rocks and the sediments are very fragile in nature. So and these lakes are expanding. So when there's extreme snowfall event, what we saw in Kedarnath, then it's enough water to burst that dam, right? But these debris covered glaciers, there might be a landslide from in the landscape, a big boulder which is a part of the which is also lying on the glacier. Because the glacier is retreating, and maybe there is a point where a big boulder is at the edge of the glacier, and interacting with the glacier and glacial lake, it can go and bump into that particular lake and it bursts. So of course it might. So if you go in the Himalayas and you just walk on a glacier, you will see all of a sudden you see a big boulder which comes right in front of you. So and that will create, it will go somewhere, right? And when, because the glaciers are retreating, so like the boulders are not moving, it is like the glacier front is retreating, and the glacial lake which is adjacent to this is expanding, and there is a point which is at the edge that it go. So of course, to answer your question, it may do that.
Thank you, sir. Thank you, sir. And so one more question, so one small one, sir. So to start off, sir, should we use optical imaging, or like you mentioned, radar data? Also nowadays there are high resolution like planet scope data, that high resolution commercial for small areas. What do you suggest?
Yeah, the thing is like you may start with optical, because this is like you see the real world in front of you using these high resolution images, and once you have a feel, you will see there is a strong advantage, because these images look very similar to the real world, so we can decipher information from that. But at some point you would realize that you need to include radar images in these regions as well, because they are often cloud cover and the weather conditions are not very great, and the solar radiation is not very consistent, so that you have to also include radar. So I think you may start with optical, but you have to use radar as well.
Any more questions or query, discussion? Dr. Sab, your talk is more related to current scenario about the climate change link.
That's right. Yeah, that's correct.
And I think that will also, that kind of the study will help us in the, like this happened in the 2-3 months back in the Joshimath, upper side of the Joshimath
area. Yeah, I was very much involved in actually, to study that glacier. That is called hanging glacier.
Okay.
So hanging glacier are very steep in nature, and it's very hard to monitor, because through remote sensing or in the field, of course not, because when you go, there are thousands of glaciers. Where to look?
Not possible.
Yeah, where to look? Like you don't know where to look. Like you can monitor some big glaciers, but this is a very small glacier hanging somewhere. But what I understand is like what happened really. So that glacier
slope is very high.
So yes, exactly. So it's very steep. So Himalayan glaciers have a slope of around 15 to 20 degrees in general. Like overall, they are very gentle. Like river river cannot be like waterfall is like a very steep, right? Like waterfall, boom, like the water goes dive. But like river is very consistent. It's very gentle. So
that is a major. I think that is the major reason of that, as you mentioned, the washout of the NTPC power project, hydropower project in the downstream area.
Yeah.
Because that is almost washout, that project is.
Yeah, absolutely. And it was not a glove event. It was like this glacier, this hanging glacier, which collapsed. It's called ice avalanche. So because ice is also staying on top of the rock. So both rock and ice, which actually fell from 5,500 meters to 3,900 meters.
Oh, so approximately
1.6
2,000 meters.
kilometer a big. So imagine a mass
Huge,
of
huge energy.
and huge energy, and actually that actually also stop the consistent river flow, and also trap water, and that was good. That was good enough to reach down the valley and created that disaster. It was horrible. So now
Yeah, really.
we are monitoring these hanging glaciers in the Himalayas now.
I think this kind of study is doing by Wadia Institute, I think so.
They also do. Yeah, yeah. So Vadia Institute of Himalayan Geology and also some other institutes, they are doing some field observations. But of course, we are talking about the deep regions where human beings don't go.
That can't
So
go.
it is very hard to actually observe and where to look. So satellite remote sensing sometimes gives you a bird's eye view, like where to look for. And then on the basis of that, like we're improving the algorithms and see how we can better our observations.
And that kind of the work can be linked with the landslide problem of the hills.
Yeah, I mean, not link, but I mean, this is also a mass movement, right? So that
Okay.
is also, yeah, it's also based on the fragility of the material, and also, how fast they are flowing and the steepness. So these are the things, yes. So all the
Because of
mass
that,
flow,
we know
mass events.
all the Himalayan hills are the very faulty joint and the joints are very weak.
Yeah,
So
yeah, yeah.
that's why there is a
Absolutely.
majorly landslide is happening in the like Uttarakhand or Himachal Pradesh region.
Exactly. Especially during the Indian summer monsoon time,
Yeah,
you see
during monsoon time specifically.
the rain triggers, yeah, the slope and makes the slope unstable.
And because of this water mixed with the soil and it will become a slurry. When the
Yeah, yeah,
slurry will flow, so how force is increase heavily.
that's right. That's correct. Yeah.
And some more question or discussion from the audience side also, participant side. That's a discussion from my side. Yeah, audience, participants.
What I hope that, like, if you are not working in that direction, after listening to my talk, maybe you just explore, what can you do, and like what topics you are interested in. There is a plenty of uh, research lines which you can pursue, for instance. And if you have questions, even in the future, I mean, you can write an email to me.
Yeah, even though with the help of these kind of the talks, the research area will be explored.
Yes, exactly. So more people are interested,
Yeah,
and so
like might be
everybody can
no
find
one is
something.
working from in this area, but
Yeah,
after listening of this talk, might be thinking about one or two be thinking this areas also.
that's right. Yeah, that will be, yeah.
That is
Very
the
good.
help. That is the benefit or help to about to the exploring the research area in the different direction in particular area.
Yeah, I mean, there is a plenty of data which we call analysis ready data, which is available for the Himalayas by all the space agencies. I would just go. I would just focus. I would suggest all the participants, if you are interested, just Google NASA European Space Agency analysis ready product, and you will see that sometimes you always don't have to start from scratch. There is a plenty of information which you can uh, start with, and then you see, when you are interested doing your PhD, you will find some gaps that you can fill from your work.
And audience, I will repeat again, audience participants have some query. Even though I will say, if you have a small query or silly query, even though sometimes we thought that query is very silly, but sometimes silly query is becoming the very big.
Anything.
So anything, whatever you like, you can discuss here.
I would say not a query is a silly query. I mean, like I heard there's like the person who asked the question is a fool once, but the person who doesn't ask a question remains fool all the time.
Yeah.
So I heard something like that. So if you have a question of any kind, I suggest to just go ahead. I'm here.
And if you want to not to ask here, want to type here, you can put your query in chat box.
I'm hanging there for the next 15 more minutes. So you just,
So I don't think so any more query from the participant side.
Okay.
And thanks, Dr. Saurav. Very interactive and very
Thank you so
interesting
much.
topic talk. I will
Huh?
say. Very interesting topic in your talk
Thank you so much.
about to the exploring the research area of the remote sensing in the different dimensions.
Yeah.
Because this dimension not much open in our country.
Yeah, sure. And I think
So in that point of view,
there's a lot we need to do.
Yeah.
And I think we need to train a lot of people. And if they are interested, I think there are several directions, where people should look at, and
Yeah.
not me, like I'm the only person, or maybe like few. I mean, glacier community in India is very, very small.
Yeah.
So if you need to expand, and we need to solve these problems, right? We need to identify these glaciers, these hanging glaciers, which might, create the similar disaster. We need to identify the location, and maybe just say to the authorities, look, man, these are some vulnerable areas where we have done some signs, and maybe like the future is, they will listen to us.
Yes, right, absolutely. And Dr. Elora, would you like to add some more, any point?
Yeah, that's true, because that this particular so far actually I have though I'm not, but I don't belong to this remote sensing and GIS field. I don't have much experience in that, but so far I have attended so many lectures based on this remote sensing and GIS. But this particular topic which you discussed today, it was really different and very interesting, because the Himalayan region you discussed, I had never been I have never thought about it even. So but that's the reason why I appreciated your presentation earlier too. And thank you for giving your time. That is really in fact we are glad to have you with us, and thank you for accepting our invitation. Thank you so much.
Thank you so much. Thank you so much for your words. And yeah, I hope for the best.
Yeah. Thank you. Yes.
Good evening, sir. This is Aditya Gupta from School of Management Sciences, Varanasi. Actually, sir, I have worked with agriculture, and I have designed a data warehouse for Indian agriculture. Was my research topic. And I'm just asking a question. Would you suggest any software by which I can visualize the agricultural data? I mean, to GIS software on which I can visualize the agricultural based data like fertilization, land seed, soil quality on or like that. Which software will be suitable if I want to visit?
There are a lot of software, but if you want to have a specific information, I think you should go, like, if there's an existing data for your study area, like the soil quality, for instance. So when we say the soil quality, it means like you can derive like soil moisture from sensing.
Actually, sir, at my earlier time, I have started the working on the map info.
Yeah, but like again, since I don't belong to that area, I would say, like, any variable you are looking for, you have to see whether how we can derive that information. I mean, software, there are plenty. So like whether, like, I give an example. If you're talking about soil, so we can derive soil moisture. Soil moisture we can derive from remote sensing data, and there's an algorithm, and there are a plenty of software for this. You can simply Google it, and then, and then you will see that you can derive that information.
Okay. I thought you are a right person. Maybe I'm just asking. I want to know that if what actually in the practice in the organization or similar organization who's working on that. Thank you very much, sir, for solving, for trying to solve. Thank you very much.
Anything more? No. Thank you.
Okay, then I think.
Thank you, Dr. Saurav, once again. Thank you.
Thank you. Bye.
Dear participants, so now we are at the end of the third day. So we will meet again on tomorrow morning.
Sir,
Yeah.
we have not shared the Google form.
Oh, I'm not prepared actually, Dr. Hello.
Okay, so can I actually I have session, sir. So can I stop this recording?
Yeah.